I've looked over the quiz results for this week's quiz on habitable zones and wanted to make a few comments about positive and negative feedback systems and how those relate to the planetary climates for Earth, Venus, and Mars. Okay, so we know that carbon dioxide is an important greenhouse gas and plays an important role in regulating planet temperature and determining overall planetary temperatures. On the Earth, we have a cycle called the carbonate silicate cycle, which helps to regulate CO2 levels in the atmosphere over the course of geological timescales. There are a number of components involved with this carbonate silicate cycle. We have, of course, the carbon dioxide that's in the atmosphere, and that carbon dioxide, that carbon, cycles through a number of different components, including carbon dioxide that's in the ocean, carbon that is eventually buried in geological sediments, and then released back out to the atmosphere. So the way this works is that outgassing of carbon dioxide from volcanic eruptions is one of the critical inputs of carbon dioxide to the atmosphere. Once that carbon dioxide is in the atmosphere, it can combine with water vapor in the atmosphere to form a weak acid, carbonic acid, essentially carbon dioxide dissolved in water. Of course, then that carbon dioxide becomes involved with the water cycle on the planet, assuming the planet has a water cycle like the Earth does. So as precipitation occurs, some of that carbon dioxide rains down onto the land surface, and because carbon dioxide mixed with water is this weak acid, that it participates in the weathering or the chemical breakdown of minerals in the land surface. So then you have things like bicarbonates and other dissolved materials that can flow off into the ocean. And in the ocean, you have a variety of chemical reactions that take place to produce various kinds of carbonates, like calcium carbonate in this particular example. And those carbonates, like calcium carbonate and other magnesium carbonate and so forth, are easily precipitated into the marine sediments, and then plate tectonics over time can bury those ocean sediments down into the crust, and then of course further plate tectonic movements can lead to the melting of that crust to form magma that again during the eruption of that magma causes a variety of causes the amount of carbon dioxide to be outgassed. So this is a process that takes place over very, very long time scales. We're talking about geological time scales here. And that cycling tends to provide what we know of as a negative feedback mechanism. Basically, with rises in temperature of the planet, so as the temperature increases, we know that that's going to speed up the hydrological cycle, it's going to speed up mineral weathering of rocks and so forth. So that increase in temperature is going to lead to increase in weathering, which is going to in turn lead to carbon dioxide being to some extent scrubbed from the atmosphere. So we're going to see reduced atmospheric carbon dioxide, which in turn will cycle back here to reduce the temperature. So that's a negative feedback. And these negative feedback processes are important in essentially acting as a thermostat for our planet Earth. So the way that thermostat would eventually work is that if for some reason we did have increases in carbon dioxide, which led to increases in temperature, we would have increases in weathering, which would scrub the carbon dioxide out of the atmosphere. Conversely, if for some reason we had a reduced amount of carbon dioxide in the atmosphere, that would lead to drops in temperature, which would lead to decreases in weathering, and then the ongoing volcanic activity would have an opportunity then to build the carbon dioxide back up in the atmosphere. So, although we know carbon dioxide levels have varied from time to time over geological history, really those levels have remained within a more constant range than we might expect without this kind of negative feedback loop providing a regulatory control. Okay, so I want to briefly touch on just a few examples of positive and negative feedback effects that have influenced temperatures of the terrestrial planets in our solar system beyond this basic carbonate silicate cycle. So in the case of the Earth, we have fairly good evidence for there being several episodes during Earth's history where planetary temperatures dropped to sufficiently for the planet to have essentially close to worldwide glaciation. These are known as this hypothesis is known as Snowball Earth. This is there's an example of some positive feedback mechanism and long-term negative feedback mechanism playing a role in here. So for a variety of reasons, which we won't go into in this short little tutorial, there are times when the Earth can be subject to an extended cold spell. Okay, a lot more serious than what it sounds. So with a long period of decreasing temperatures, of course, one of the effects of that is that the north and south polar ice caps are going to expand. We see this during regular periods of glaciation. But one thing that's going on is as those ice caps are expanding, the albedo of the planet is changing. The degree to which incoming solar radiation is absorbed is decreasing. With more and more ice, that means more and more of the incoming solar radiation is reflected out to space rather than being absorbed. So in this case, we have essentially a long-term decrease in global temperatures leading to increased glaciation, leading to reduced solar absorption, reduced absorption of incoming solar radiation, which is going to then magnify that decrease in temperature, which is only going to allow the glaciers to expand more and more, which is going to reduce even further the amount of sunlight that's absorbed by the Earth, which is going to further reduce the temperature. So you can see that this process is a positive feedback loop that changes throughout this loop, reinforce the rest of the loop, and The result is that, as we talked about, the bulk of the planet can be um, covered by glaciers that extend down from the poles. So that would be the positive feedback loop of this example. However, once you do have that sort of worldwide glaciation, if it ever did get to the completely worldwide, there's some debate about that. One impact of that would be that it would cut off the ocean from the atmosphere. So because the ocean is isolated from the atmosphere, the ocean can no longer take up carbon dioxide from the atmosphere. And also with so much of the land surface covered by glacial masses, clearly we're going to get much reduced weathering. And reduced absorption of carbon dioxide into the ocean. Meanwhile, volcanoes are going to be cranking along as they normally do, and you're going to have volcanic eruptions that are large enough for that outgassed carbon dioxide to be released up into the atmosphere through the ice sheet that's covering the planet. So once you get into the Snowball Earth situation, there is a natural way that the Earth will eventually break out of it, because the volcanoes are going to continue to pump out carbon dioxide. Because of the ice layer, there's not going to be any way for the ocean to remove carbon dioxide. And eventually, over time, you're going to build up more and more of a greenhouse effect in the atmosphere. And eventually that's going to lead to a greenhouse-induced hothouse effect in the atmosphere that will eventually melt those global ice coverings. And over time, the Earth will eventually revert back to its more normal glacial and interglacial kind of situation. We've already talked in class about Venus being subjected to a runaway greenhouse effect, resulting in it being the very hot planet that it is today. So I won't go through that again, but there were, again, two sources of positive feedback loops in here. The first one involving increases in temperature, leading to increased evaporation from Venus's early oceans. So increased water vapor from the oceans into the atmosphere, leading to a stronger greenhouse effect, which in turn raised the temperature, which led to more water evaporation and more greenhouse effect. And as we talked about before, this process would eventually result in the loss of any early ocean that Venus might have had, with all of the water vapor up in the atmosphere. And of course, once Venus lost its oceans, it would have had no means to sequester carbon dioxide from the atmosphere, as we talked about with the carbonate-silicate cycle on the Earth. So at that point, continued volcanic eruptions would continue to pump carbon dioxide into the atmosphere, with Venus having no way to scrub that carbon dioxide out of the atmosphere because of the lack of a ocean reservoir to bury carbonate minerals into. So between all of the water in the atmosphere, as opposed to being in the ocean, and continued buildup of carbon dioxide because of no way to scrub it out, then Venus has a what you might call super greenhouse effect, leading to the very high temperatures that we see on Venus today. So now I just want to quickly preview Mars, since we're going to be moving into looking at Mars for the next couple of weeks in class. It's likely that Mars has, in opposition to Venus, had a runaway refrigerator effect. As we'll talk in the class in the next couple of weeks, there's good evidence that early Mars might have been fairly Earth-like, or at least much more Earth-like than it is today. So early Mars, had potential to have a thick atmosphere with greenhouse effect and with the water vapor and carbon dioxide in the atmosphere, and a fairly Earth-like hydrological cycle and temperatures that, while they might not have been totally Earth-like, were probably warmer than Mars is today. And it's clear that over time, Mars has transitioned into a cold desert planet, essentially, with a very thin atmosphere and no extensive deposits of liquid water in the ocean. Clearly no oceans, no lakes, no rivers on modern-day Mars. To some extent, this might look a little bit like the Snowball Earth, but really it is a different kind of phenomenon. For reasons we'll talk about later, Mars probably began to lose its atmosphere to space with the loss of its magnetic field. And so as the atmosphere of Mars thins, so thinner atmosphere, that would lead to a reduction in the amount of greenhouse effect that Mars's early atmosphere would have provided. And then, of course, with a reduced greenhouse effect, we would have seen reduced temperatures. And in the case of Mars, temperatures got low enough that the decreases in temperature actually led to further thinning of the atmosphere as atmospheric components like carbon dioxide and water basically froze out of the atmosphere. And the more those materials froze out of the atmosphere and thinned the atmosphere, then that would lead to a further reduction in the greenhouse effect, leading to further decreases in temperature, leading to more freezing out of the atmosphere. And so in this case, you've got a positive feedback mechanism, but it's not leading to increased temperatures, it's actually leading to decreased temperatures. So, quick take-home message from this short little tutorial is really about the importance of these feedback mechanisms. We have two basic types. We've got negative feedback and positive feedback. Negative feedback negative feedback systems basically are regulatory systems. They have mechanisms built into the system that some kind of perturbation, like increased weathering or decreases in the amount of carbon dioxide in the atmosphere, lead to further changes that tend to ameliorate or those perturbations and return the system back to some kind of equilibrium. And the carbonate silicate cycle is a prime example of this kind of negative feedback system that provides that regulation. In the case of positive feedback mechanisms, these tend to be non-equilibrium. They tend to force systems further and further away from some initial conditions. So these are destabilizing mechanisms. And the runaway greenhouse effect on Venus, the early cooling in Snowball Earth, and the potential runaway refrigerator effect on Mars are all examples of where initial changes led to mechanisms that amplified those changes and led to a destabilizing change in the conditions over time.